tells that sorry, transaction could not be processed, please take your card. So that option has to be kept, otherwise people will keep on infinitely waiting. So the utility of the watchdog timer is that it gives the flexibility to the user to operate with the counter, but at the same time keeps a check on it whether the transaction has been performed within a certain time slot or not. Otherwise, it resets the whole thing. So unlike a normal timer in which the timer itself generates the interrupt, that is, operation has been, timer itself generates an interrupt signaling that certain interval of time has elapsed. A watchdog timer just operates in the opposite sense, in the sense that it is expecting some signal from outside on some event, and then it resets itself to 0. If it doesn't receive the external interrupt, it will back off for a certain period of time, which is equivalent to the max value of the counter, and then it generates some overflow or any other signal signaling that it has not received the interrupt within that specified time interval and resets to 0. So these are the registers which you typically use to keep track of. So this time register basically keep track of the max value of the counter. Okay. So for example, suppose I want to count up to 11070. I stored this in the time register, and the scale register is basically the up counter or down counter, whatever you choose, which counts from 0 up to the max value. Yeah. So the notion is that I have to find out the count value for the specific interval of time. It is a 16-bit timer with 2 microsecond resolution. Then when it counts from 0 to 2 to the 16 minus 1, it counts up to this, it counts for this interval of time. When it counts, if you don't put any max value of the counter, it could have count from all zeros to all ones. So the time interval corresponding to all zeros to all ones is 2 into 2 to the power 16 minus 1, because it's a 16-bit counter. Then you have to, but that is more than 2 minutes. So you count the period of time that is equal to 2 minutes and subtract that value from this max value, so that you put that value in the time register.
So that's not equal to 2 minutes. From the total time you are subtracting 2 minutes and keeping it in the time register.
No, I mean the notion is that you choose a value of x such that this difference is equal to 2 minutes for this problem. And whatever be the time interval, you choose a certain value of x such that this difference is equal to such that you count up to an interval of time that is equal to 2 minutes, right? Now in most now these are the things which you have not done as a part of your DLP, in the sense Normally, when we develop practical embedded systems, we only need to encounter about these kinds of problems. That is, in DLP, you basically learnt about single purpose circuits with minimum or no programmability. But consider the case of this 2 minutes thing which you raised. For one application, I need to wait for 2 minutes. For some other application, I need to wait for 10 minutes. For some other application, I need to wait for 5 minutes, whatever be it. So, should I go for custom hardware for each and every case? That's not possible. Or moreover, for example, if you take the case of this ATM, I may initially choose that I will wait for an interval of time that is equal to 2 minutes, and 1 month later I feel that if I allow the system to wait for 2 minutes, there's a very long queue outside the ATM counter. I should reduce the interval of time to 30 seconds or 45 seconds. Right? So, it has to happen through some programmable chip only. Otherwise, I have to build the entire hardware from the ab initio level. So, that's why these kinds of things, where you load some value into some counter and allow the counter up to some to go to some max value, or start with that max value and come down to 0 and again go back to the max value. These kind of programmable things are facilitated through general purpose programmable, application specific instruction set processors like the microcontroller. So, if you see your ATmega16 data sheet, which is already there in your courses portal, you will see that if you see the block diagram, and I have also shown you the block diagram 2-3 classes back, you must recollect that there was a watchdog timer block in the microcontroller. So, that watchdog timer is basically used for all these type of applications, where you need to, where you are expecting some interrupt from outside. Otherwise, you back off for a certain period of time and reset. Clear? Now, coming to the architecture of the timer in AVR microcontroller, which you are using in your lab. So, over here in AVR microcontroller, you are basically using the microcontroller is having two timers, timer 0 and timer 1. Each timer is controlled, has to be controlled by a clock signal, but there for each timer we can see that there are 8 options of choosing clock signals of different frequencies. One option is that you are not using any clock signal, which means the timer is not operating, that corresponds to this 0. Then you have an option in which you choose the system clock or some clock frequency derived from the system clock, which is a fraction of the clock frequency. So, the microcontroller is provided with a 10-bit timer counter prescaler. The prescaler therefore produces 4 clock frequencies. One is 1 by 8 times the clock frequency, one is 1 by 64 times, one is 1 by 256 times, and one is 1 by 1024 times. So, these are the 4 clock frequencies that are produced by the prescaler. Okay. Now, these 4 frequencies are also available to the to this multiplexer, and apart from that, you can also provide external clock signals through this T0 and T1 inputs. Either you can use the clock signal or its inverse. Now, in many clock, I mean, it specifically for certain applications. So when these clock generators typically generate a clock pulse, it is either it is typically a pulse followed by a gap. That means mark and space format. That means first it provides the pulse, then there is the time interval for 0, then 1, then 0, like that. On the other hand, for certain applications, you may require to have the logic 0 first followed by logic 1, right? And you need to work on the active edge of the first pulse. So in that case, such clocks are, such demarcations are necessary. So now let's see the block diagram of the timer counter block in Avier family microcontrollers. So as I said that you have an option of choosing between the internal clock or the external clock. So here, you are providing this external clock through T0 or T1 input, indicated by Tn over here, n equal to 0 or 1, and then you choose the active edge through the edge detector, whether you will choose the positive edge or negative edge of it. Otherwise, you can also choose your internal you can also choose your system clock frequency or part of it from the prescaler. So the prescaler either provides the system clock or a fraction of the system clock frequency. Now that clock signal is sent to the control logic. The control logic, as you can see, has got 3 outputs: clear and direction. The count output is used to indicate to the timer counter to do the counting. The clear signal indicates to the timer counter to reset to 0, and the direction indicates whether I shall be doing up counting or down counting. The timer counter keeps on updating itself and produces the count value into the data bus. Now this counting, unless you have, now depending upon the mode of counting, I may count up to the max value of the counter or some top value being stored in the output or OCR. So corresponding to timer 0 and timer 1, I have output capture 0 and output capture 1. And then I compare Now either I can go up to the top value using this OCR 0 or OCR 1, or depending upon the mode I ignore what is there in the OCR 0 or OCR 1 and can count up to the max value. So I will teach you the different modes at which this operate, and then suppose I am using it in a mode which allows me to check the value of OCR 0 or OCR 1. So when I find a matching occurs, I give some signal to the waveform generator to produce a 0 or 1, and accordingly you get a train of pulses at OC0 or OC1. In case the counter counts up to the max value and again resets to 0, overflow is set through TOV 0 or TOV 1, timer overflow flag. So these are the registers used for timer and counters in the AVR microcontroller, that is the timer counter register. I mean, your clocked system, the specific purpose for which you are using a system basically decides the frequency at which you will be operating, right? So as you have seen that in depending upon the application, you choose the amount of time for which you need to wait for certain event to take place, or generate an event after a specified interval of time, and that interval of time varies considerably from application to application. So that interval of time also guides me to choose the clock frequency at which I am going to operate. Now regarding this interval of time, I am left with two options. I basically have two options to work with. One option is, I don't really write a block of code, I simply need to program the timer counter to start counting from 0 up to some value, and then the timer counter should generate an interrupt at the end of the count process, right? In that case, I don't really need to go on calling some interrupt service routines or so. I can purely do it with the help of the timer counter. So it will count from 0 up to some max value and again reset to 0 like that. Now that max value depends upon the interval of time for which you need to wait. So if you just do it with play with your own clock frequency only, then you are highly restricted in terms of the clock frequency. You have to choose the max value accordingly, and in many cases it may be such that the max value of the counter is sufficiently less so as to address your timing requirements. So now if I work on clock signals with lesser frequencies, I can go on increasing the maximum interval of time for which I can wait, right? But still it cannot solve all the problems. That is, suppose you work with the lowest frequency of the prescaler and still the max value which you can reach with the counter do not satisfy your timing requirement still, then the next option is, every time your timer goes to the max value and resets to 0, every time your timer goes to the max value and resets to 0, you have to the overflow flag is generated, and based on the overflow flag you have to call an interrupt service routine, and you keep track of number of times you call the interrupt service routine. So for a certain finite number of times the interrupt service routine is being called, your interval of time for which you were supposed to wait expires, and then the whole thing is reset. what time you need to wait for and all that. And so preferably we first try to resolve the issues at the hardware level, which means without calling the interrupt service routine, we try to resolve it with prescaler and timer counter only, failing which we go for calling the interrupt service routine approach. That's the typical way we go through. So there are timer counter control registers, TCC are 1A and 1B, which basically controls the timers in several ways. That is the mode in which the timer is going to operate, up counting or down counting, and then there are various modes of pulse width modulated waveform that is being generated. So next you have the output compare register or OCR, which basically is used in certain modes of operations of the timer counter, in which the timer counter can start counting from 0 up to the value of OCR, and then in some modes it will reset to 0 when it reaches a value equal to OCR. Otherwise it basically sets or resets the output control pin and generates the PWM waveform. So one of the possible applications of PWM is, I'll actually come to PWM a little later today. So now suppose this is a sinusoidal waveform, right? Now what are the different ways I can represent this sinusoidal signal in discrete time? You have learnt about continuous time and discrete time signals in SNS class. So this is basically a continuous time signal, right? Now, what are the different ways I can represent it? I can represent it actually we mark it like this arrows. Actually it is not really arrows but some small pulses of very small width. They are basically pulses of very small width which we consider to be almost equal to 0. So this is basically you are using a train of pulses and multiplying it with the sinusoidal signal to get a pulse train whose amplitude is varying in accordance with the instantaneous amplitude of the sinusoidal signal. So this is called a pulse amplitude modulated waveform.